we're going to look at lesson 4.2, adding and subtracting polynomials. This is something you did last year in math too, so hopefully this is just review. All right, so we're going to start with task 1. Identify and analyze monomials and polynomials. A monomial is a number or a product of a number and variables with whole number exponents. All right, whole number exponents. Remember what a whole number is. They're positive and they're not fractions. So a whole number, positive, and not fractions. All right, so a polynomial is a monomial or a sum of monomials. All right, here's some examples of monomials. -10, x to the 4th, 3x, y to the 5th. Even though this is a product of stuff, it's still a monomial because it's one term. All right, polynomials that are not monomials. So this is two terms, x plus 2, that's two terms. Here's 1, 2, 3 terms, and here's 1, 2, 3, 4 terms. So these are all considered polynomials. All right, monomials and polynomials can be classified by the exponents of their variable terms. All right, so the exponents of the variable terms. The degree of a monomial is the sum of the exponents of the variables in the monomial, and the degree of a polynomial is the greatest degree of its monomial terms. Polynomials are often written in standard form, in which the term of the polynomial ordered from greatest degree to least. When written in standard form, the coefficient of the first term is the leading coefficient. All right, so this is some important stuff here. The degree of a monomial is the sum of the exponents. The degree of a polynomial, not a monomial, is the greatest degree in the leading coefficient. Okay? All right, so let's look at some examples here. So here you have a polynomial, 4 minus 3x. We need to put it in standard form, going from highest to lowest exponent. So they rearranged it here using commutative property. So we got -3x plus 4. This is in standard form. And the degree comes from the highest monomial from the exponents, from the sum of the exponents. So there's only one variable, so one exponent of 1. That's why it's a degree of 1. The leading coefficient always comes from the term that's in the front from standard form. So it has to be in standard form to determine the leading coefficient. All right, so the next polynomial, rewrite it. There's 2, 1, 0. So you're going exponents from greatest to least. That puts it in standard form. And the degree is the highest exponent here, so that's a 2. The leading coefficient is -2. All right, so you got a polynomial here. The highest degree is 7, and then 5, 4, 3. So these have to be rearranged to put it in standard form. So this is your leading coefficient, so the degree is 7, and the leading coefficient is 4. All right, it says select the examples of expressions that are not polynomials. Okay, so what's not a polynomial? Well, this is not because it's negative. This one is, it's not in standard form, but it is still a polynomial. This one is a constant, but it's still a polynomial. And this one is not. So it says find the ones that are not polynomials. So the first one and the last one are the two that are not polynomials. All right. B part says place the polynomial in standard form. All right, standard form means we have highest exponent to least. So we're going to go 5, 4, 3, 2, 1. So look at the exponents. So here's 5, 4, 3, 2, and to the first power. All right, so standard form always puts them in order by exponents. All right. Identify the degree of the leading coefficient of the polynomial you just put in standard form. All right, if we look at the polynomial we just put in standard form, the highest degree is a 5, so that would be a 5th degree. The leading coefficient is negative, which means that's a -1. So the leading coefficient is a -1. All right, C part says if k is a real number, then k is a polynomial expression. What is the degree of the polynomial k? All right, so if k is a real number, there's no variable, it's just a constant, so the exponent would be 0. Explain your reasoning. All right, anything to the 0 power, really don't know how to explain that, except there's no variable there, so you have to have a 0 exponent. If there's an x, it would be assumed to be an exponent of 1. And then x squared, quadratic, x cubed would be a 3, and so on and so on. But if there's no x, then that means there's a 0 exponent, which means x to the 0 power is 1. 1 times k is just your real number. So that's the best way I can explain it, which was this question here where it says explain your reasoning. All right, and then the last one says choose a polynomial that has 3 terms, a leading coefficient of -4, and a degree of 5. So this is 2 terms, can't be that one. 1, 2, 3, 1, 2, 3. All of these have 3 terms. Now we need a leading coefficient of -4 and a degree of 5. So it has to be B or the second one there. All right, that is all for task 1. Task 2, add and subtract polynomials. All right, to identify and analyze monomials and polynomials. All right, so it says number 2. I don't know where number 1 is, but number 1 must have been on task 1. So number 2A, use the distributive property to add the monomials -3x squared y and 9x squared y. Select the answer. All right, so they're calling this distributive property. I usually call it like combining like terms, because if they have like terms, x squared y and x squared y, that means we can combine the coefficients. So we can combine these -3 and 9 and give me 6x squared y. So the variables don't change when you add monomials. Now when we multiply, then your exponents would change, but not when we're adding. So the reason they're calling this distributive property is because you can take the x squared y out of both of these terms, and then that leaves, let me see if I can write it down. It leaves it, it's just going to look like the distributive property for you. All right. All right, so what you're doing is for distributive property, kind of pulling out like terms and factoring out everything that's the same, because these are the same in both of these. Then we're just going to add the other parts together, which is the -3 and 9. So that's how we get 6x squared y. And because it can be rewritten in this form is why it's called distributive property. Because if you use distributive property, you get -3x squared y and plus 9x squared y. All right, now need to make sure we check that and we can move on to the next question. All right, can the distributive property be used to add the monomials 8x cubed y squared and 2x squared y? And the answer to this one is no, because x cubed can't be added with x squared. So because these are not like terms, those do not have common factors, then you cannot combine those. And that is my reasoning for that. All right, given that a and b are real numbers and n is a whole number, write ax to the n plus bx to the n as a monomial. All right, so we're going to have a plus b, and then that's going to be x to the n power. Again, when you're adding or combining like terms, they're calling this distributive property, but really you're just pulling out that these have the same variable with the same exponent, and that's called distributive property. All right, so use the result to find negative 3x to the fourth plus x to the fourth. Both of these have x to the fourth, so we can combine these. This one doesn't have a coefficient, so it's assumed to be a 1. So it's going to be negative 3 plus 1, which is negative 2. And x to the fourth does not change. All right, the next one says when the polynomials this and this are added, which pair of monomial terms can be added? All right, 3x can be added to anything else with an x squared, so nothing. 5x to the fifth can be added to something with an x to the fifth, and the constant terms can be added to another constant term. Why might it be helpful to write the polynomial in standard form before performing the addition? Well, remember, standard form means it goes from highest exponent to lowest, and if you can combine them based on the same exponents, it would be helpful to be in standard form. So it says you can automatically add together the first term, second term, and so on. You can identify like terms because they are ordered from greatest to least. You can change the exponents of the variables, and you can put the coefficients in order from greatest to least. All right, so the first one says you can automatically add first term, second term, and so on. That's not true necessarily, because what if one's missing a term? What if it goes x cubed and then x and there's no quadratic term? So you can't automatically add them just because they're in standard form. This one says you can identify like terms because they're ordered from greatest to least. So that one makes the most sense. You can change the exponents. You can't change a problem, so you can't do this. And you can put the coefficients in order from greatest to least. Well, that's not going to be helpful because you're doing stuff with the exponents. So really, standard form needs to be exponents greatest to least. All right, that is task 2. If you have any questions, let me know.